Imagine a tiny bubble, smaller than a pinhead, fizzing with purpose. Inside, carbon dioxide, one of our planet's biggest troublemakers, is being transformed. With a zap of electricity and clever chemistry, it becomes something useful, clean fuel. This is the cutting edge of chemical engineering, turning pollution into power. What if the gas warming our planet could be captured and converted into the liquid energy that powers our world? This is electrochemistry, using electricity to drive chemical reactions, specifically the carbon dioxide reduction reaction, or CO₂-to-fuel. We're taking CO2 and, with energy and smart design, turning it into energy-rich molecules like ethanol or ethylene. The magic happens inside the bubble, creating the perfect environment for this transformation. For centuries, burning fossil fuels has disrupted the planet's carbon cycle. Now, scientists are working to reverse that, capturing CO2 and, using renewable electricity, turning it back into fuel. When that fuel is used, the CO2 can be captured and recycled again, a closed, sustainable loop. Let's explore how this technology works, why CO2 is so tricky, and how tiny acid bubbles could change our future. It's a journey from pollutant to solution, all starting inside a microscopic, fizzy world. Science rules. Carbon dioxide isn't inherently bad. It's essential for life. But the problem is the sheer amount we've added to the atmosphere. Since the Industrial Revolution, burning fossil fuels has released ancient carbon, overwhelming the planet's natural balance. Think of the atmosphere as a bathtub. The tap is on full blast and the drain can't keep up. The result? A rapidly warming planet with more heat waves, storms, rising seas, and disrupted agriculture. Scientists agree. We must urgently cut CO2 emissions and manage the excess already in the air. The scale is immense, billions of tons per year. Stopping emissions isn't enough. We need bold solutions to deal with the carbon overload. That's why transforming CO2 into something valuable is so exciting. It's about turning a liability into an asset. The decisions and technologies we choose now will shape our planet's future. The time for action is now. Traditionally, we've tried to bury CO2 underground, carbon capture and storage, or CCS. But CCS is energy-intensive, expensive, and not foolproof. Enter carbon capture and utilization, or CCU. Instead of burying CO2, we use it to make valuable products like fuel. This turns CO2 from waste into a resource, creating economic incentives for capture. Fuels made from captured CO2 are carbon neutral. Burning them simply returns recently captured carbon to the air. If powered by renewables, the cycle is truly sustainable. These synthetic fuels could revolutionize hard-to-electrify sectors like aviation and shipping. It's a shift to a circular carbon economy, designing waste out of the system. By treating CO2 as a resource, we close the loop and mimic nature's cycles on an industrial scale. This isn't just waste management. It's a fundamental rethinking of energy and industry. The future is circular. So why isn't everyone turning CO2 into fuel? The chemistry is tough. CO2 is a stable, low-energy molecule. Breaking its bonds takes a lot of energy. Enter catalysts, substances that speed up reactions without being consumed. Metals like gold and silver can turn CO2 into carbon monoxide. But copper is the real star. Copper uniquely catalyzes the formation of complex, energy-rich molecules like ethylene and ethanol. The process dissolves CO2 in water, apply voltage to a copper catalyst, and use the resulting electrons to break bonds and build new fuels. The challenge is precision, maximizing fuel yield while minimizing unwanted byproducts. The right catalyst and conditions are key to making this work efficiently. That's the heart of CO2 reduction. A major challenge is the chemical traffic jam at the catalyst surface. The reaction shifts the local pH, causing unwanted carbonate buildup that clogs the process. The solution? Acid bubbles. Scientists use membranes to feed protons directly to the catalyst, keeping the local pH low and stable. This prevents clogging and keeps the reaction running smoothly. Tiny acidic bubbles create perfect microenvironments for CO2 conversion. This targeted approach boosts efficiency and tackles two bottlenecks at once. It's a powerful example of microscopic chemistry solving big problems. The core device is an electrochemical cell, or electrolyzer, with three main parts. The cathode, with copper catalyst, is where CO2 reduction happens. The anode splits water to provide protons and oxygen. The electrolyte, often a proton exchange membrane, lets protons move between electrodes while keeping products separate. Electrode design is crucial. Porous, sponge-like structures maximize surface area for reactions. Gas diffusion electrodes allow CO2 to reach the catalyst efficiently. The process feeds CO2 to the cathode, water to the anode, and apply renewable electricity. Water splits at the anode, sending protons through the membrane and electrons through a wire to the cathode. At the cathode, CO2, protons, and electrons meet on copper, producing valuable fuels. The result? An elegant, engineered system for efficient CO2 conversion. Every component is optimized for one goal, turning waste into fuel. This is the future of clean energy. The system is ready for scale. How do we measure success? Scientists use key metrics. Faradaic efficiency. What percentage of electricity actually makes the desired fuel? Overpotential. The extra voltage needed to drive the reaction. Lower is better. Current density. How much fuel can be made per area per time. Higher means more productivity. For real-world impact, we need high efficiency, low overpotential, and high current density. Recent advances in electrode design and pH control have boosted performance dramatically. Stability is crucial. Catalysts must last thousands of hours. Selectivity matters too. We want one product, not a messy mix. The challenge is to excel in all these areas at once. That's what chemists and engineers are racing to achieve. The finish line is in sight. Turning lab breakthroughs into world-changing tech takes time, but progress is rapid. The next step, seamless integration with renewables, using solar and wind to power CO2 conversion. This stores clean energy as liquid fuels, solving renewables' intermittency problem. Future systems will combine capture and conversion in one device, pulling CO2 from air or flue gas and making fuel in a single step. Advanced catalysts, designed with AI, will boost selectivity for high-value products. Startups are scaling up, building pilot plants to prove this works outside the lab. This is more than a clever trick. It's a paradigm shift in how we view carbon and energy. It's a real path to a sustainable, circular economy. The challenges are big, but the science is sound and innovation is accelerating. The humble bubble could be the hero that fuels our clean energy future.